Welcome to this video. My name is Mark Scythian. The date today is August 12th, 2025. So in this lecture, we are going to cover battery physics pertinent to lithium polymer and lithium-ion battery chemistry. So there's 4 questions to answer here. The first one is, what is the maximum potential energy of the lithium-ion battery? So we can use these specifications on the battery to solve all the questions here. So the first step is we have to access the current capacity, which is the 25,800 mAh milliamp hours. So that's the current capacity. And for practicality's sakes, we can divide it into 1,000 milliamp hours per amp hour. It's just solved for the amp hours. So that's the base current capacity value. So we have to apply the maximum discharge rate of 5.5 C. So if this was a lithium-ion battery for, let's say, an electric vehicle, the 5.5 C would be the maximum throttle on the accelerator. So we'll apply 5.5 C times the 25.8 amp hour current capacity, and so we get 141.9 amp hours at 5.5 C discharge. So the voltage, DC voltage per cell for lithium polymer and lithium ion battery chemistry only is 3.6 volts per cell. So we can multiply 110 cells, which are connected in series, because we are using a constant current application, but the system is designed to wire the battery cells and the connection to the inverter and then to the motor in series. So 110 cells times 3.6 volts DC rates the battery at 396 volts DC. So we multiply the voltage of the battery times the amp hour discharge rate at 5.5 C, and we calculate 51,192.4 watt hours is the maximum power output, but we are concerned with energy as in potential energy, not power. So energy is not power. Very important concept to understand, which we're going to cover the conceptual descriptors of power and energy. So make sure you watch this video to its completion, because then there won't be an argument or any confusion if you understand the concept. So we have potential energy, which is measured in joules or in joule value, and a joule is equal to a Newton meter in the metric system. And then if we evaluate how many newtons force is equal to 1 pound force, it is 4.45 newtons. And then 1 meter is equal to 3.28 feet. So if we slice a piece of the newtons value and convert it to the pounds, it would be a fraction like 0.224. So we would multiply 1 over 4.45, 0.2247 times 3.28 feet. And then this implies a conversion ratio from joules to foot-pounds, a multiplier of 0.737 foot-pounds per 1 Newton meter or 1 joule. So remember, a joule is also equal to a Newton meter. So both potential and kinetic energy are measured in joules or foot-pounds. Now, when we are dealing with power, power is force times distance divided by time. So in the metric system, that would be force newtons times meters, or meter distance divided into time, or Newton meters per second. So that would be a power value because it's over the function of time. However, energy is not over the function of time. Energy or work is just the force times the distance, or in this case, joules or foot-pounds. So that's the potential and kinetic energy values. So if we were to divide, let's say, the kinetic energy over time, then we would get joules per second or watts. So Newton meter is joule, and joule divided by second is a watt. So you get Newton meter per second or foot-pounds per second for the US system of measure. So we convert it over to just joule per second. So 1 joule per second is 1 watt of power, whereas 1 joule is just 1 Newton meter, and that could either be a kinetic or potential energy value. So these two are not the same. All right, so we continue on solving the first question. We have 51,192.4 joules maximum potential energy, because we've taken the time function out of the power maximum value. And then we know through the conservation of energy that the kinetic energy is equal to the potential energy in a closed system. So therefore we can isolate the joules maximum potential energy as 51,192.4 joules. And if we convert this to its US system of measure equivalent, that is then 51,192.4 joules times 0.737 foot-pounds per joule, and that would be 37,728.8 foot-pounds of maximum potential energy. So we can solve question 2 in concert here, because the law of conservation of energy states that energy cannot be created or destroyed, but only can be changed in form. So this is also known as the first law of thermodynamics, which is the conservation of energy. So therefore, the maximum potential energy is equal to the maximum kinetic energy. So the answers for question 1 and 2 are one and the same. So now we continue on and solve question 3, which is what is the DC electrical power output in watt hours or kilowatt hours when the discharge rate is set to 3.3 C. For example, an electric vehicle's accelerator is depressed slightly and the battery discharge rate is measured at 3.3 C. So first we get the base value of current capacity, so we'll just divide the 25,800 milliamp hours into 1,000, and then multiply the 25.8 amp hours times 3.3 C, and we calculate 85.14 amp hours of current discharge. So that's 85.14 amps for 1 continuous hour, and then we multiply that times the battery voltage rating, so we get a watt hour value at 3.3 C discharge of 33,715.44 watt hours, or 33.7 kilowatt hours as the electrical power output at 3.3 C discharge. And then lastly, if you want to evaluate the performance of your battery, see if it's in good condition, question number 4 is what is the internal resistance in ohms of the battery if it is powering a DC powered AC power inverter, which converts DC to AC, at a 2.3 C discharge rate at an electrical efficiency of 86.4%. So that might be just a slight press on the accelerator. So it moves it from 1.5 C to 2.3 C. And then that is the efficiency, the electrical efficiency of the transfer from the battery to the inverter. So that it's 86.4% on average. So we can again find the base value, current capacity, 25.8 amp hours. We can multiply this times 2.3 C, and then times the battery voltage, and then times the electrical efficiency transfer from the battery to the inverter, and then we calculate 28,302.82 watt hours are flowing to the inverter. So that's the effective power, and that has a capability to flow for 1 continuous hour, 28,302.82 watts. However, if we isolate it within an hour, it would then be 20,302.82 watts. So then we access the DC electrical power equation, which is P DC electrical power in watts is equal to I current in amps times E voltage, DC voltage. And then instead we solve for E, so we can calculate the effective voltage at inverter after correcting for the efficiency losses. So that has been calculated. So now all we need to do is solve for the effective voltage to the inverter, and again we'll calculate the amp hour discharge at 2.3 C. So again, it's practically 59.34 amps if it's within an hour. So it is, in this case, that's the check based on predication of the system. So 20,302.82 watts divided into 59.34 amps, and this yields a effective voltage going to the inverter of 342.14 volts DC. So our load voltage, or voltage transferred from the battery to the inverter, is 342.14 volts DC. And so to calculate the battery internal resistance, we first have to calculate the battery's internal voltage. So we can just subtract the load voltage from the battery voltage rating, and so we have an internal voltage remaining of 53.86 volts DC. So now we can access Ohm's law, which is E DC voltage is equal to I current in amps times R resistance ohms. So E is equal to IR, Ohm's law for DC circuits. And so if we solve for R, then that is the voltage divided by the current. So that is how we can calculate the battery internal resistance at 2.3 C discharge rate for the given battery. So we have 53.86 volts E. And lastly, be careful to identify the concept, because we divide that by I, but there's no guesswork here because the battery cells are connected in series and the battery is wired to the inverter in series. So series circuits maintain constant current. So that means during the load applied to the inverter of 342.14 volts DC, the current across the inverter and the battery under a load is constant. So that means if we were to identify what E actually would be from a conceptual standpoint, we have a constant current across battery and inverter at 2.3 C discharge. So we take 2.3 C discharge and multiply it times the 25.8 amp hours. We calculate 59.34 amp hours, which is within an hour, so it is practically 59.34 amps. So this is the I value. This is the constant current across the battery and the inverter while they are energized. This is very important because then once you identify a constant, there's no variation. You have the accuracy reached. So now you can just divide the internal voltage into the constant current, and we yield a battery internal resistance of 0.907 ohms of internal battery internal resistance. So thank you for watching this lecture and have a great day.